Hello everyone, my name is Haozhe Zhang. As the agenda shows, I will present our first idea, turn the machine learning problems into database problems. I will show this idea with three examples: linear regression, support vector machines, and mutual information. When looking at the machine learning problems through database classes, everything looks like a batch of aggregates of varying structure complexities. For instance, consider the linear regression model and its variants like ridge linear regression and polynomial regression. They would use square loss functions as their objective functions, which are convex and differentiable. So we can optimize them using gradient descent. The computation required by the models can be made up by simple sum product aggregates over the attributes in the input relations, possibly with group bias. This means the computation workload of these machine learning models can be captured by these in-database queries. In addition, many other tasks like computing the covariance matrix, learning decision trees, mutual information, and arc-means can also be captured by these simple group by aggregate queries. However, for those models using non-polynomial loss functions, these aggregates are not enough. We need to add in addition a filter, which here we express it using so-called additive inequalities. Think of them as weighted sums of attributes that appear in a comparison with a constant. They could be thought of as theta joins, and for this sort of theta joins, we recently came up with a novel technique to evaluate them efficiently. Non-polynomial loss functions are used for a broad class of models. For instance, linear support vector machines would use hinge loss, support vector machines in general would use epsilon insensitive loss, robust linear regression use Hubbard loss, ordinal regression models and ordinal PCA would use ordinal hinge loss, and quantile regression models would use scaling loss. For some of these cases, the objective function is convex but non-differentiable. In this case, we would use subgradient descent, where the subgradients can be captured by the aggregate queries of the form we show here. For our database example with 39 attributes, out of which about a third are categorical, we get over 800 aggregates, for instance, to learn regression models. The queries for a particular model would have same aggregates but over different attributes, and they are all expressed over the same join of the database relations. This suggests that there are ample opportunities for sharing computation of the queries within a batch. I will next show you three examples of turning the machine learning problems to query batches. Let's look at the ridge linear regression model first. The linear regression model is defined by this linear function of two vectors, theta and x, where theta is the vector of parameters we want to learn, and x is a sample from the dataset. The model computes the prediction for this sample x by the dot product of the two vectors, which means the sum of the corresponding theta and data value x. We use this notation to denote the dot product. To get the training dataset D, we apply the feature extraction query to the input relations. In D, we have the features and the label represented by columns, so a tuple from the training dataset D would have the attribute vector x and its response y. To learn the parameters for this linear function, we need to find the parameters that minimizes this objective function. The objective function has two components. One is the least square loss, and one is the regularizer. For this least square loss, for each sample in the dataset, we compute the prediction for that sample using our model and compare it with the label to get the prediction error for this sample. The error for this model is then the sum of the square of all errors from all samples in the training dataset. The aim is to find the parameters that cause the minimum errors. The second component, the L2 norm regularizor, is to prevent overfitting, which is to avoid the model being too biased to the training dataset so it does not generalize to other data. This slide shows graphically the idea of least square loss function. The dots on the plot are the data points in the training dataset. For example, this data point shows when x is 1, the corresponding y value is 3 at here. The goal is to find the optimal parameters of a linear function that can estimate the y values for new x values. In other words, find the regression line that fits the data points. This red regression line does not fit the training data points perfectly. For every data point, there is a distance from the y value from the training dataset and the regression line, which are represented as the green lines. The aim is then to find the regression line that minimizes the length of all green lines. In other words, minimizes the sum of the square losses. Finding the optimal parameters can be done by repeatedly updating theta in the direction of the gradient until convergence. This is the gradient of the objective function, and we keep updating the parameters theta using the gradient until a fixed number of times or the parameters do not change much. The constant alpha here controls the amount of each update. This optimization is the main computation workload of linear regression models. How to get from the optimization to curry batches? We have this model reformulation idea. We look at this objective function j and its gradient, and we think, can we rewrite this formula in a way so that we decouple the parameters theta from the computations we have to do over the data x and y in the training dataset? If we can decouple the data-dependent and data-independent computations, this data-dependent computation is just an in-database computation, which we can do efficiently. Let's see how we can rewrite the formula. This is the original objective function with the square loss function and the L2 norm regularizor. We can open the quadratic bracket and push the sum into the bracket. The first term of opening the bracket is this dot product of theta and x times dot product of theta and x, which gives us this term. In this term, I push the sum past theta to have this term sum of x transpose. We can push it past theta because theta is constant for all the tuples in the dataset. The second term of the opening the bracket is 2 times dot product of theta and x and minus y. We can push the sum into the dot product because theta is constant for all the data in the dataset. And the third component is the quadratic of y. And this x times x transpose is the outer product of the two feature vectors, so it is a matrix. And the sigma is the matrix that sums all the matrices. The y here is a scalar, so y times x is a vector, and c is the vector that sums all the vectors. And y squared is a scalar, so sy is also a scalar. These three components are the data-dependent computations. The power of this transformation is that we decouple these data-dependent computations from the formula, so we can compute them efficiently using in-database queries. By the way, if we put the three data-dependent components to form a matrix, we can see this matrix is very much related to the covariance matrix. It is not exactly the covariance matrix. We need to take away the means from the product, though this means if we can compute these data-dependent components efficiently, we can also compute the covariance matrix efficiently. Covariance matrix is very useful for a lot of other things. I will show you now how to represent these data-dependent components as batch of queries. Consider the matrix sigma. We need to compute one query for each entry, which is to sum the product of the attributes xi and xj of all tuples in the dataset. In the case both attributes xi and xj are continuous, we have both xi and xj here to be scalars, so the result for this entry is scalar. We can use the sum product query select sum of xi times xj from D to compute the value for this entry. D is the result of the feature extraction query over the input relations, in other words, the training dataset. What if one of the attributes is categorical? For example, if we have a categorical feature xi to be Ct and a continuous attribute temperature, and the value of Ct here is London and the temperature is 25 degrees, London times 25 degrees does not make sense. We need to use one-hot encoding for this categorical attribute, so the value xi is not a scalar, but a vector with the size of the number of cities in the dataset. In other words, the size of the domain of the attribute city. And in this vector, all values are 0 except the value for London is 1. The product of the vector xi and scalar xj is a vector, so the result of this entry is also a vector, which sums xi times xj over all tuples. To compute this vector, we can use the query with group by of xi. This query means for each xi value in the dataset, we sum the xj values over all tuples in the dataset. Each sum value corresponds to an entry in the result vector. Similarly, for the case that both xi and xj are categorical, we have both xi and xj to be vectors, and the outer product of them gives us a matrix. To compute the matrix, we use the query with the group by of both xi and xj, which computes for each xi and xj pair the number of appearance of the pair in the dataset, and each number corresponds to an entry of the matrix. So this is how we express the data-dependent component using batch of queries. We have looked at the rich linear regression model. Let's now turn to the mutual information. The mutual information of two attributes measures the degree of the correlation between them. Mutual information is useful in many machine learning tasks. For example, it can be used to identify attributes that are highly correlated with the label attribute, so that we can drop the unrelated attributes to reduce the dimension of the model. It can also be used to learn the structure of Bayesian networks, such as Cholio trees. For two attributes x1 and x2, the mutual information of them is defined as this. In this formula, P1 is the probability mass function of feature x1. P1 of a given x1 is defined as the number of tuples that has this x1 value over the number of all tuples in the dataset. Similarly, P2 is the probability mass function of x2, and P12 is the joint probability mass function of x1 and x2. We want to transfer the computation of these probability mass functions to database queries. Let's see how we can do it. We will use 4 count group by queries. The first one computes the count of tuples in the dataset, and the second query computes for each x1 value the count of tuples in the dataset. In other words, for each x1 value, the number of tuples that has this x1 value. With these 2 queries, we can capture the probability P1. We have the number of tuples with this x1 divided by the number of tuples in the dataset. Similarly, to capture the probability P2, we need the number of tuples with this x2 divided by the total number of tuples. So we need this query. And to compute the last probability, we need the number of tuples for this x1, x2 pair divided by the total number of tuples. To capture this, we have the last query, which is to group by both x1 and x2. Now let's look at the formula for computing the mutual information. If we replace the probability in the formula, we can get this formula. This is how we capture the computation of mutual information using database queries. The final example I would like to discuss is support vector machines. A binary support vector machine is used to separate the data into 2 classes. For this dataset, we have square data points and circle data points. The objective of the support vector machine is to find the decision boundary, defined as this, to classify the data points. There are many possible decision boundaries that separate the data points. Which one should we choose? If we look at the example, we can find some data points are harder to classify than others, like these 3 data points. We call them support vectors. The goal of support vector machines is to find the optimal decision boundary such that the margin between the support vectors of the 2 classes is maximized. Support vector machines find the optimal decision boundary by minimizing the objective function defined here. It is for a binary classification problem, so the label of a symbol can be either -1 or 1. The objective function is similar to the one for the ridge linear regression, except here we use the hinge loss function instead of the square loss function. This hinge loss function makes the objective function non-differentiable, so we have to optimize the objective function using subgradient-based updates. I will show next we can capture the required computation by a batch of queries. This is the objective function. We first rewrite the max function to this product, 1 minus y times the dot product of theta and x times this condition term. This condition term here means it is 1 if the condition is satisfied, otherwise it is 0. Next, since we know y is either -1 or 1, we decompose this term to 2 cases. In the case y is equal to 1, we replace the y by 1, so we have this term. And symmetrically, for the case y is -1, we replace the y by -1 to get this term. Since y can be either -1 or 1, which means only one of these two conditions is satisfied, only the term that satisfies the condition will stay, and the other one will be 0. It is like an if condition. If y is 1, then we choose this term, otherwise we choose the other one. The next step, we open the brackets. By opening this bracket, we have first 1 times the two conditions, which is the first term here. Then we have the dot product of theta and x times the two conditions. We can push the sum and the conditions into the dot product since theta is independent from the data. Like what we did for the linear regression model, this is to decouple the data-dependent and data-independent computations. We call the first term S1 and the second term C1. And similarly, we do the same transformation for this term to get S2 and C2. Now let's see how we can express these data-dependent components as batch of queries. Let's first look at the queries for S1 and C1. S1 is a scalar. It counts the number of tuples that satisfy the two conditions. The count can be computed by the query select sum1 from the database. To capture the two conditions, we can use the where conditions y equals 1 and this inequality. This kind of condition is called additive inequality, and as I mentioned, we can evaluate it efficiently. C1 is a vector. The only difference between C1 and S1 is that we have an x in the definition here. This means instead of counting the number of tuples like in S1, we sum the values in vector x over the dataset. So the result is a vector. For each entry in the vector, we add an aggregate sum of the values for that attribute to the query. We can add it because they are under the same conditions. The queries for S2 and C2 are similar. We just need to change the conditions. And with these values, we can do the computation for the support vector machines efficiently. This is how we capture the support vector machines using batch of queries. To summarize, this slide lists the models we have considered so far and the further ones under consideration. All of them can benefit from structure-aware computation. Thank you for your listening. We are happy to take questions.